All right, today we're going to start the second lecture of chapter number 3. And our learning goals for today is to define projectile motion, describe the curved path followed by a projectile, apply kinematic equations on the projectile motion. Now, in chapter number 2, we dealt with kinematics in one dimension, and then we dealt with the free fall in one dimension. But now you can basically throw something at an angle. So, for example, you can throw this at an angle theta naught and at initial velocity v naught. Now, as we did in chapter number 1, you can take component of this vector. So this vector here will have an x component, which is v naught cosine theta naught, and it will have a y component, which is v naught sine theta naught. Now we say theta naught here, or theta 0, that's at t is equal to 0. This angle is going to change, because when you get to the highest point in your trajectory, you will find out that the object's going to fall down and you only have an x component of the velocity. You're not going to have a y component of the velocity. So this angle here, theta 0, is going to change through your projectile motion. But that's what you have at the beginning here. Now, in this case of projectile motion, once the object leaves your hand, like what we did in the free fall, you're no longer in control. It's under the influence of what? It's under the influence of gravity. So remember, when you want to write your acceleration vector, we said that the acceleration vector will have an x component plus a y component plus a z component. Now, in this situation here, when you have a projectile motion usually is in two directions. Try throwing something, you will find it will go vertical and horizontal. So you can regard them as two-dimensional motion. And you know, when you have an x-axis, you can x, z, and you can also have the z here, which will be pointing out of the screen. But in a projectile motion, you can look at something that we call vertical, horizontal, so you don't need the third axis here. So I'm going to eliminate the z component here. And you have only the x and the y component. Now, this will be the direction of your gravity. It will be downward along the y direction. So your ax will be 0 because you will have no acceleration along the x-axis, but your ay will be minus g. And we dealt with that when we dealt with a free fall in one dimension. So right away, this is, if you want to look at your acceleration, the ax will be 0, and the ay will be minus g. And you know, it's two-dimensional motion. You're also going to have a velocity, which will be vx I hat plus vy j hat. And you will also going to have a position vector, which is x I hat plus y j hat. And remember, you can also look at it as rx I hat plus ry j hat. So that's how you describe your projectile motion. We did with all of this. We have kinematic equations, okay, that we developed. We're only going to describe the kinematic in two dimensions. But one thing that you have to remember, and when you basically throw something at an angle, it will follow trajectory like this. That's what we call a trajectory here. And the trajectory will have a horizontal part and it will have a vertical part, okay? And that's why it will be moving that way. Now, to illustrate this point more, you can basically look at dropping the red ball here, or you basically fire the yellow ball straight this way. Now, when you release from rest, this ball is going to fall down this way. It's falling down under the influence of gravity. Now, when you fire the yellow ball in this direction here, which is horizontal, the ball would like to move in this horizontal direction, but the gravity will try to bring it down. Now, if you basically concentrate on, let's say, this position here and this position here along the y direction, you will find it's the same. In this, it's basically released from rest and it's falling down under the action of gravity. In this situation here, you're firing the ball horizontally, but along the y direction, it's like a dropping. Okay, you want to go straight this way, but the gravity will bring you down as if you're releasing this from rest to fall down. And of course, in this situation here, you only have y, but in this situation here, when you get to this point, you will have x and y. You will have two components. And this is the difference now between a projectile motion and one-dimensional free fall. In a projectile motion, it will move horizontal and it will move vertical. And this is what you have in the yellow ball. It's moving horizontally and the gravity is bringing it down, and that's why it's moving vertical. So if we look at our projectile motion in two dimensions, and as I told you, when we look at this, you're going to consider it's two-dimensional motion. The x is horizontal, the y is vertical. Okay, so you have here what we call horizontally, that's the x, and what we have here vertically, and that's the y. So you project something this way at an angle theta 0, and we say here velocity v0. Of course, you can break your initial here into v0x, which is your x component of the velocity, and the v0y, which is the y component of your velocity. You can say that this is equal to v0 cosine theta 0, and this will equal to the v0 sine theta 0, like when you're taking components of a vector. Now, as I explained to you in the previous slides, when you look at your acceleration, you can take it as ax I hat plus ay j hat. And I told you the ax is 0, but the ay is equal to minus g. And that's what we have here. Now, when you want to look at your velocity, and we dealt with that in chapter number 1, we said that Vx is equal to V0x plus Ax t. But if you look at your x component here, your Ax is equal to 0, so this is gone, which means that your Vx is not going to change. It's going to stay as the initial x component of your velocity. And that's basically what carries you horizontally. But if you look at your Vy, it is the V0y minus GT. And you will find out that at the maximum height, your Vy is going to be 0. And then it will drop down. But when you look at your velocity, it is the Vx I hat plus Vy j hat. That's why when you look at this now, this is your Vx at this location here, but it's not going to change. It's going to stay the same because your Ax is equal to 0. Your Vy here is going to change because you have the minus g. At the maximum height here, your Vy will equal to 0, but your Vx is going to stay as it is. That's why in a projectile motion, the velocity at the highest point in your trajectory is not 0 because it has an x component. But it is right to say that the y component of the velocity at the highest point is 0. But it's not like the 1D free fall. In 1D free fall, at the highest point, the velocity is 0 because you only have a y component, a vertical component. But in the case of projectile motion like this, when you look at your trajectory, the x component is not going to change because the ax is equal to 0, but the y component is going to change, and that's why you say at the highest point, the velocity is not 0, but the y component of the velocity is 0. So as you can see here, that at the highest point, you still have a velocity, but the y component is what is 0. So if we want to describe the projectile motion, if we look at the x direction, we say the x direction has constant velocity because the ax is equal to 0. And the y component, it's a free fall, and it has constant acceleration, where ay is equal to minus g, which is equal to minus 9.8 meters per second squared, and we explained that when we dealt with the free fall. Now, in 2D now, you're going to deal with a position vector, which will have an x, so it's r position vector equal to r0 plus v0t plus 1/2 at squared. And v here will be the v0 plus at, where v0 is a vector which has an x and y component, v0x plus I hat plus v0y j hat, and also the ax. So whenever you want to look at your position at any point, it will be basically described by a position vector and a velocity vector. Your acceleration, it's already taken care of. It is 0 I hat plus minus 9.8 j hat. And that's basically your acceleration. So when we look at the description of how an object moves as a projectile motion in 2D, okay. For the x direction, we have a set of equations. The first equation that we deal with is that Vx is equal to the V0x plus Ax t. But along the x direction, the Ax is equal to 0. You're no longer in control. And that's why this drops out. And your Vx will equal to V0x. And the V0x is equal to V0 cosine theta 0. So along the x direction, your velocity is going to stay the same, the initial one. It's not going to be different at all. And that's why we say that the Vx from this equation here, it's going to equal to the V0x, and it is constant. So the x component of your velocity in projectile motion is not going to change. It's going to stay the same. Now, when it comes to your x component of the position, you know that when we dealt with that, we said that x is equal to x0 plus v0 xt plus 1/2 ax t squared. And of course, the ax here is equal to 0. So you end up with x is equal to vx0 plus v0 xt, and that's what you have here. So this is basically your x direction or horizontal direction. Ax is equal to 0. Your vx is going to equal to v0x, which is equal to v0 cosine theta 0, and it's going to stay the same. And your position will equal to x0 plus v0 xt. When you come to the y direction, and I already told you that you take the initial component of your velocity, which is v0y, which will equal to v0 sine theta 0. And your ay will equal to minus g, which is minus 9.8 meters per second squared. Now, if you look at your y component, vy will equal to the v0y plus ayt. And we did that when we did with a free fall in one dimension. You're replacing the ay with minus g, and that's why here you have your vy equal to v0y, and v0y is equal to v0 sine theta 0 minus gt. And this gives you your velocity in the y direction. And we dealt with that in chapter number 2 when we dealt with with free fall in one dimension. And your y will be y0 plus v0 yt minus 1/2 gt squared. And we used another equation. We can only use it when we talk about the v squared. We cannot write this in component because it's squared. So we can use it only as x component or y component. So for the y component here, we have vy squared equal to v0y squared minus 2g delta y, and delta y here, it's y minus y0. So this equation here will take care of the y component for you. This equation here will take care of the x component for you. Finally, you can write your position r, which is xi squared plus yj squared. If you want to get the distance, which is the magnitude, so it will be the square root of x squared plus y squared. Your v will equal to the vxi hat plus vyj hat. The vx is always going to be the same. The vy, you obtain it from here, depending on where the time and so on. And if you want to get your speed, which is the absolute value of your velocity, it will be basically the vx squared plus the vy squared. Now, if you want to get the direction, and you do that from the velocity, because that's where the velocity is changing, and you take tan alpha will equal to the vy over vx. Even though this is going to stay the same, the vy is changing, and that's why we started with theta 0. Theta at t is equal to 0, but this theta is going to change as we go in time. This basically describes the projectile motion. A projectile here, it's what we call 2D free fall. Okay? We dealt with it in chapter number 2. It's only in one dimension, but here in 2 dimension, the horizontal part, which is the x, is not going to change. I mean, the vx is not going to change. The x is going to change, because your ax is equal to 0. But along the y, that's how the v and the y are changing. And your a is constant. It's equal to minus 9.8 meters per second squared. Is this clear? Any question on this? So when you look at your initial velocity, so you see here we have v0, and v0 here means the speed. So we're just putting the magnitude, and it goes at some initial angle. We call it theta 0, and this is of course above the horizontal. So in this case, you will have a v0 sine theta 0, and here you will have v0 cosine theta 0. Now in this case here, your theta 0 is equal to 0. So this is basically your, that's here the v0x, and this one here the v0y. Now when you start this way, you're moving horizontally, and with the speed v0. So the v0x here will equal to the v0, and the v0y will equal to what? Will equal to 0, because you're not moving along the y. Now in this situation here, if you throw it down relative to the horizontal with theta 0, so in this here you will have the v0 cosine theta 0, and that will be the v0x. And this one here, the v0y will equal minus v0 sine theta 0. If you're just considering this angle, you measure this angle here. You don't measure it relative to the positive x-axis. You're just taking this angle here. So you have to include a minus sign here. That's the starting point. And then use your equation. Okay. And the set of equations that you have, the x0 or your vx will equal to the v0x, is not going to change, and your x is equal to x0 plus the v0x times t. That's it. That's the x here. Y, the vy will equal to the v0y minus gt, and your y will equal to the y0 plus v0yt minus 1/2 gt squared, and you can also say that the vy squared equal to the v0y squared minus 2g times y minus y0. And that will take care of the y, and that will take care of the x, but you have to look at your initial starting points here, and you decide. In this case, that's your vy0 and your v0x are positive. In this case, you only have a x component of the velocity, and in this case here, the vx is positive, but the vy is negative. Then you solve. The way you solve problems, you're going to choose coordinate system, meaning where is your x and where is your y. Okay. And I told you, always can choose your initial points at x0 is equal to 0, y0 is equal to 0. But in some situation, you may basically do not do that. In most cases, you do that. Okay. Then you take components x and y. That means you're going to take the vx0 and the v0y. Then you're going to analyze the motion for the horizontal, which is x, the vertical, which is y, and then you solve for the equation if you have what? If you have the time. And that's the strategy to deal with this. So let's apply that to some examples. And the first example here, you have a motorcycle rides off the edge of a cliff with horizontal velocity of magnitude 9 meters per second at 0.5 seconds after it leaves the edge of the cliff. Find the motorcycle position and distance from the edge of the cliff. And then the B, they want the velocity, but they want it after this time. So now, this is the starting point here. So you choose X and Y. So this is your X, okay, and this is your Y. That's the first step. Where is your X and where is your Y? Y will be vertical, X will be horizontal. The starting point here at t is equal to 0, it is advisable to use x0 is equal to 0 and y0 is equal to 0. So you're done. They tell you that he's moving horizontally. So this is your initial velocity here, which only has an x component. That's why we say that theta 0 here is equal to 0, because he's starting horizontally this way. They give you the speed here, which is equal to 9 meters per second. And they tell you of magnitude, velocity of magnitude. So I say V0 here. I did not put an arrow. That means I'm just taking the speed. The V0x, which is equal to V0 cosine theta 0, and cosine 0 is equal to 1. You get 9 meters per second. And the Vy0, it's very obvious. It's going to equal to V0 sine theta 0, and theta 0 is equal to 0, and sine 0 is equal to 0. That's why you get 0 meters per second squared. So you have your V0x and V0y. And we chose that the x0 is equal to 0 and the y0 is equal to 0. Now they tell me here after 0.5 seconds, so after t is equal to 0.5 seconds, what is my x? What is my y? Your x, remember, you said that x is equal to x0 plus v0 xt plus 1/2 ax t squared. But we said in projectile motion, this is equal to 0, so it's gone. So that's what you have. X is equal to x0 plus v0 xt. So you start with here, the x0 is 0, and the v0x is 9 times 0.5, and you get 4.5 meters. So that's your x position after 0.5 seconds. For the y, y is equal to y0 plus v0 yt minus 1/2 gt squared. Your y0 is 0. The vy0 is 0 as well. So all you have minus 1/2. G is 9.8 and t squared, and it gives you here minus 1.2 meters. And again, it's minus. That means it's below. So now your position has an x component, which is 4.5 I, and y component, which is minus 1.2 j hat. If you want to get your distance, how far are you? Well, it will be the square root of x squared plus y squared. So the square root of 4.5 squared plus minus 1.2 squared, and that gives you 4.6. Now, when we want to look at the velocity, you know that the x component is not going to change. The Vx is equal to v0x, which is equal to 9 meters per second. So it's going to stay the same. Now, when you come to your Vy will equal to V0y minus GT. The V0 is equal to 0 minus 9.8, and t here we put 1/2 because we said it is the 0.5 here. And that gives you minus 4.9 meters per second. So after 0.5 seconds, your velocity now, the x component is 9 I hat, the y component is minus 4.9 j meters per second. And that's basically how we apply this problem. Is this clear? Any question on this one? Here we have another example. A ball leaves a bat of a player with a speed of 37 meters per second at an angle of 53.1 degrees. Find position, velocity of the ball at t is equal to 2 seconds. Again, when you start at t is equal to 0 here, your v0 is equal to 0. Your vy of 0 is equal to 0. Now your initial speed here is 37 meters per second, and theta 0 is equal to 53.1. Of course, this will be your x, this will be your y. So now you're going to take the components of your initial velocity here. And of course, you're going at an angle above the horizontal. So your v0x will be v0 cosine theta 0, which is 37 cosine 51.3 degrees. And that gives you 22.2 meters per second. The v0y will v0 sine theta 0, which is 37 sine 53.1, and it gives you 29.6 meters per second. Now, they ask you after 2 seconds, what is the position and the velocity? For x, x is equal to x0 plus v0 xt. x0 is 0. The v0x is the x component, which is 22.2 times 2, and gives you 44.4 meters per second. That's the x component now, after 2 seconds. The y component, y is equal to y0 plus v0 yt minus 1/2 gt squared. The y0 is 0, 1/2. The vy0 is equal to 29.6 times 2 minus 1/2. 9.8 times 2 squared, and this gives you 39.6 meters. So your position now after 2 seconds, it's 44.4 I hat, which is your x component, plus 39.6, which is the j component, and of course we put the units here in meters. Now when it comes to velocity, projectile motion, ax is equal to 0, ay is equal to minus g. Your velocity is not affected at all along the x-axis, so the x component of your velocity is going to stay the same, which is equal to the v0x, which is 22.2 meters per second. The vy will equal to v0y minus gt, which is 29.6 minus 9.8 times 2, and you get 10 meters per second. So you're still going up. Okay. You did not reach the maximum yet and went down. And your velocity here will be 22.2 I hat plus 10 j hat meters per second. Is this clear? Any question on this? That's how you apply your knowledge of kinematics under the influence of gravity in 2 dimensions, which is horizontal and vertical. Now, in this example here, it is the same thing, but they ask you the time when the ball reaches the maximum or the highest point. So they need this time when it reaches the maximum height. Now, you know one thing, that at the maximum height, your Vy should equal to 0. So Vy equal to V0y minus Gt. At maximum height, your Vy should equal to 0. So 0 will equal to the V0y minus Gt. So you can rewrite this equation here. You will say that the V0y will equal to Gt, because you can take this to the other side. Now you're interested in T. So your T will equal to the V0y over G. And the V0y, which is 29.6 over 9.8, and this gives you 3 seconds. So to reach the maximum height here, it will require 3 seconds to reach there. Now it will take another 3 seconds to reach this point here as well. So you can say the time for the trajectory will be 6 seconds if we ask you to do that. But remember, if it hits here, but if it continues, then you have to add that time as well. Now in this, it is the same example, but they ask you the range. And the range here meaning the horizontal distance from the start. That means all of this distance here. What is this range? You know that your x is equal to x0 plus v0 xt. Now your x0 is equal to 0. So your r, it will equal to the v0 x times t. And we put 2 here just to indicate that it's the time to reach when it gets to this point here. Now, we can do that from the previous, and I told you we will multiply the time twice, but you can also use this equation here, where we say that y is equal to y0 plus vy0t minus 1/2 gt squared. Your Vy will equal to 0, but when you reach this point, your y is equal to 0 as well. So you're starting from y0 equal to 0, and you end up at y equal to 0. So 0 equals 0 plus v0yt minus 1/2 gt squared. Now you can rewrite this equation here by taking this to the other side. So you'll have 1/2 gt squared equals, and I can put 2 here, vy0t. So you can cancel the t here with the square. So if you want to get your t2, you multiply this by 2. So you cancel this here and you multiply this by 2. You divide by g, and that's why your t2 here will equal to 2 vy over g. And if you remember in this slide here, we said that t1 is equal to v0 over g, and I told it take 3 seconds. So it will take another 3 seconds to come here, and that's basically what we're doing here. It will, in projectile motion, it will take the same time to go to the maximum height. It's the same time to get back. So as if you're throwing something in one dimension, it will take the same time to go up, and it's the same time to come down. But this is, of course, it's carrying out by the x, and that's why you have here the 2t. So your range here will equal to x0 is equal to 0 plus your v0x with 22.2 meters times 6 seconds, and that will give you 133.2 meters. So in this example here, you basically got your position after and velocity after 2 seconds. We looked at the time reached the maximum height, and we also looked at the range. Okay. Any questions so far? Any questions? Now in example 3 here, they give you a general situation, okay, where you're starting with some initial velocity at an initial angle theta 0, h here meaning the maximum height, and r here meaning the range. Okay. And when you do that, you can fire now between 0, so you can fire horizontally, or you can fire up at 90, but you can choose any angles between 0 and 90 degrees. For a given theta 0, that means you don't change that, you keep that. What is the value of theta 0 that will give maximum height and it will give maximum range? So you can imagine that you have here a cannon and you fire from the cannon and you can vary the angles. Varying the angles, when you take smaller angles, it will give you a higher height, but maybe smaller range. Smaller angles maybe give you higher range, but smaller heights. So that's what we want to find. Okay. So let's analyze that in general. Okay. Now, in general, what you do is you choose your x and y, and you're given v0 and theta 0. So you take your x component, which is v0 cosine theta 0. Your y component is v0 sine theta 0. H is the maximum height, which we can say the maximum y, and r here is the maximum range. Now, you can choose your x 0 is equal to 0, your y 0 is equal to 0. So let's look at the y component first. We want to get to the maximum height. And we dealt with that in one-dimensional freeform. So we look at y squared equal to v0y squared minus 2gy minus y0. Now, at maximum height, y will equal to h. And of course, your y0 is equal to 0. At maximum height, your vy will equal to 0. Only the x component of your velocity is equal to 0 at maximum height. So out of this equation here, the v0y will equal to v0 sine theta 0. So you're squaring that. So you have v0 squared sine squared theta 0 minus 2g times h minus 0. So you have minus 2gh. You can take this to the other side, and what you will have 2gh will equal to the v0 squared sine squared theta 0. Now you're interested in h. So your h will equal to the v0 squared sine squared theta 0 over 2g. Now you have sine theta 0 here. And you know that sine will go between 0 and 1. Or it can go between minus 1 and 1. But in this case, you cannot, you're on top of horizontal, so you cannot go below that. You're firing up. The maximum value when the sine squared theta 0 is equal to 1. And that only happens when theta is equal to 90 degrees. Which makes sense. To achieve the maximum height, you will fire up, not at an angle. So this will give you the maximum height. Now, how about the maximum range? Okay. Well, when we deal with the maximum range, Okay, I want the time to basically reach the end of my trajectory, and we already dealt with that. Remember when we said that y equal to y0 plus v0 yt minus 1/2 gt squared, and you start from y equal to 0, we end up at y equal to 0. So what this time, the time that we need there, we already done it in the previous example. So 0 is equal to 0, v0 yt minus 1/2 gt squared. Now I want to get t here. This is 0, this is 0, so I have 0 here. I can take t as a common factor. So I have t, I have v0y minus 1/2 gt. Now I want to get the time, and that either to get 0, that t is equal to 0, and that's at the start. So that's, I'm not considering that. But the other t is when vy minus 1/2 g is equal to 0. And that basically will give me that my t will equal to 2vy 0 over g. And we already then did that. So it will equal to 2v0 sine theta 0 over g. And that's the time to reach this point here, which is the range. Now you know that your range is equal to v0 plus x0 plus v0 xt. The x0 is 0, and the vx0 is v0 cosine theta 0, and your time now is equal to 2v0 sine theta 0 over g. So your range, you have v squared here, you have v0 and v0, it will be v0 squared times 2 sine theta cosine theta over g. Now, you know that there is a rule when you're dealing with trigonometry. Sine theta 1 plus sine theta 2, it's equal to sine theta 1 cosine theta 2 plus sine theta 2 cosine theta 2. So imagine if I make theta 1 theta 0 and theta 2 theta 0. So you will get here sine theta 0 cosine theta 0 plus sine theta 0 cosine theta 0. So sine of 2 theta 0, because I told you make this theta 0 and this is theta 0. So sine 2 theta 0 will equal to 2 sine theta 0 cosine theta 0. So the 2 sine theta 0 cosine theta 0, it can be replaced by sine 2 theta 0. So your r here will equal to v0 sine 2 theta 0 divided by g. And r will be maximum when the sine here equals to 1. And sine equal to 1, it's sine of 90 degrees. So 2 theta 0 has to be 90 degrees, which makes theta equal 45 degrees. So the maximum range here you will get when you fire at an angle of 45 degrees. Probably you did this in high school, but this is the reasoning why. Again, this equation here and this equation here, you can only use it in this situation when it's symmetrical. That means you start from y equal to 0 and you end up at y is equal to 0. If you start from y equal to 0 and you end up somewhere below y equal to 0, you cannot use this range equation here. You cannot do that because there is still extra time to go and you have to compensate for that. But that works if you go from y equal to 0 to y equal to 0. Is this clear? Now here we have Another example. We're doing more examples here to apply these. You throw a ball from window 8 meters above the ground. The ball leaves your hand with a speed of 10 meters per second at an angle of 20 degrees below the horizontal. How far horizontally from the window the ball will hit the ground? So that's your y, that's your x, that's your starting point here, t equal to 0, x 0 is equal to 0, y 0 is equal to 0. Your v is at 10 meters per second, but it makes an angle of 20 degrees. Now it will reach the ground here. So if you look at what you're given in the problem, x0 is equal to 0, y0 is equal to 0. Your y final, when it comes here, that's your y, you have an x final here. That's what we want to find. And your y final here, the window is 8 meters above, so it's equal to 8 meters. And that's why we say minus 8 here, because it is minus below the point where we said y is equal to 0. And your v speed is 10 meters per second. Theta 0, we chose here to be minus 20 because it's below your horizontal. Your v0x is equal to v0 cosine theta 0, so it's 10 cosine minus 20 and gives you 9.4 meters per second. The v0y is v0 sine theta 0, which is 10 times sine minus 20, and it gives you minus 3.4 meters per second. Now your range, where x is equal to x0 plus v0 xt, and that's what you want to find out. And of course, this will be equal to 0. You already know this value, but you need to get the time to reach this point here. And the time, you can use this equation, y final equal to y0 plus v0 yt minus 1/2 gt squared. Y final is minus 8. y0 is equal to 0 minus 3.4t minus 4.9t squared. You can take these to the other side, so you have 4.9t squared plus 3.4t minus 8 equal to 0. You can put this in your calculator for a quadratic equation. It will give you t is equal to 0.9 seconds and t is equal to minus 0.6. And of course, this is wrong. Time should be positive. So that's the time needed to reach this point here. The y is equal to minus 8. So you put that in your range where this is equal to 0. So the Vx0 is 9.4 meters per second. You multiply that by the time, and it will give you 9.2 meters. So your x final here will be 9.2 meters. I think these are enough examples to illustrate how to look at a projectile motion. Is this clear? We have here a few questions to deal with. The first question here in the figure below, a skier flies off the ramp. Which of the following is correct? The acceleration at point G is less than point A. The acceleration at point H is 0. The acceleration at point H is more than at point B. The acceleration at G is the same as I and H. And of course, the answer here is given in red. So that's the right answer. Now, it is a free fall. As soon you leave this point, that's it. You're no longer in control. Your AX is equal to 0, and your AY is equal to minus G, which is minus 9.8 meters per second squared. That's it. So it doesn't matter. Your g is going to same, but you can say that the y component of your velocity at the highest point could be 0. But the acceleration is the same, so you have to be careful when you ask question like this. In this question here, our projectile is launched at an angle at 30 degrees angle above the horizontal. Ignore air resistance. The projectile's acceleration is greatest. Now, the answer here that we have, misleading. The acceleration is the same, but non-zero at all along the trajectory. That's it. If an object leaves your hand and it becomes a projectile, it's ax equal to 0, ay is equal to minus g, and ay will equal to minus 9.8 meters per second squared. That's it. So again, you have to be careful. At the highest point in the trajectory, your velocity is not 0, but the y component of your velocity is 0. But your acceleration is going to stay what? It's going to stay the same. Is this clear? The last question that we're going to deal with here. Okay. A zookeeper fires a temporizer dart directly at a monkey. The monkey lets go at the same instant that the dart leaves the gun barrel. The dart reaches a maximum height p before striking the monkey. Ignore air resistance. When the dart at p, the monkey, where will be the monkey? Okay. So remember, you fire and the monkey lets go. And they will meet at point C. So as the monkey is falling down, this will basically go trajectory, like he fired straight this way, but you know that's not going to go straight that way. Because of what? Because of the gravity, and it will be a trajectory like this. And of course, if they want to meet at the same point, so you have choices here. Is at A higher than B, at B the same height as this, at C, so I will leave this for you to think about and tell me what is the right answer. So what we did today, in summary, we looked at projectile motion. I told you you can always regard the projectile motion as two-dimensional motion. One horizontal, one vertical. And we said the horizontal can be regarded as x, and the vertical regarded being at y, and the ax will equal to 0. That's your acceleration. The ay will equal to minus g. And this basically will give you the x position because there is no acceleration there. This will give you the y position. And your velocity in the x component will always stay the same as v0 cosine theta 0, but the vy will equal to the v0 sine theta 0 minus gt. And that's how you basically look at a projectile motion in 2-dimension, or we can say this is 2D free fall motion. Is this clear? Any question on this? Good.